Okay, so let's examine the frequency response of our lossy gyrator circuit. So we've got our input voltage source, we've got some parallel resistance, some parallel capacitance, and a branch with an inductance in series with a resistance. RP, CP, L, and RS. We've got an input voltage and we're measuring the current flowing in here, and if we do this we'd find that the Z of this circuit is equal to RP in parallel with 1 over S times CP and parallel with RS plus S times L. Solving for this circuit, we would find that the impedance was equal to RS divided by CP times L times S times L over RS plus 1 divided by S squared plus S times 1 over RP times CP plus RS over L plus RP plus RS divided by RP times CP times L. And what we would see with this circuit is, if we were to plot the impedance, we see that we have a 0 and we would have 2 pole frequencies. So at DC, the value of the impedance, or the magnitude of the impedance, would be equal to RP in parallel with RS. When we reach this 0 frequency, and we could say that the 0 frequency, omega Z, is equal to RS over L. The impedance would start to increase at 20 dBs per decade. So this is a 0 frequency. At a resonant frequency, which would be equal to the square root of RP plus RS over RP CP L, assuming that RP is much, much larger than RS. At our resonant frequency, we would get 2 poles that would cause a roll-off of minus 20 dBs per decade. And of course, this is plotted on a log of omega scale. Looking at the phase response, what we would see would be something like this. At DC, we would have no phase shift because we have a purely resistive component. When the 0 frequency was reached, or just before the 0 frequency was reached, we would see this phase shift go to 90 degrees. The impedance is increasing with frequency, so we can say this region is inductive, or the circuit looks like an inductor. Just before the resonant frequency, the phase shift would change to minus 90 degrees, and it would stay there throughout all higher order frequencies, and we would say that this would look capacitive. In other words, the impedance is decreasing with the increase in frequency, so it looks capacitive. Now, thinking about this in terms of our bandpass filter, this looks very similar to the bandpass filter that we were looking at the other day, or the RLC circuit that we were looking at the other day. And so we can also think of a definition for quality factor. So an alternate definition for quality factor that we didn't look at the other day is simply to take the ratio of the imaginary part of the impedance over the real part of the impedance. In other words, we're looking at the energy storage capacity of the circuit, the imaginary portion, divided by the energy dissipation portion of the circuit, the real portion of the impedance. In other words, reactance over resistance. Now this isn't a very accurate definition for quality factor once we pass the self-resonant frequency, especially for passive circuits, but it will work below the self-resonant frequency of the circuit. So if we take this definition of quality factor for the prior circuit that we were looking at and isolate the imaginary part and real part, we would find that the quality factor of our circuit would be equal to omega L over R sub S times RP divided by RP plus RS times 1 plus omega L over RS, this quantity squared, times 1 minus RS squared times CP over L minus omega squared L CP. And we could find that basically this quality factor is the product of three separate quality factors, Q1 times Q2 times Q3. And for our active inductors, what this means is Q1 quantifies the quality factor at low frequencies. Q2 accounts for the finite output conductance of the MOS or BJT devices that create our GMs. And Q3 accounts for the cutoff frequency behavior of the GM source. In other words, the fact that our transconductor has finite current gain at some frequency. Alright, so what we would say is that Q1 is a low frequency quality factor and Q2 and Q3 are due to higher frequency components of the signal. If we multiply all these Q's together, we would get some kind of practical quality factor for the circuit or some kind of practical bandpass behavior for our circuit. We'll solve some examples of gyrator circuits in class on Wednesday.